here a few items. One of them is the exam. The other one is the answers. This one I can auction off starting at $1,000. This one, the bidding here starts at $100,000. This is the answers. Okay, let's get serious. There are 8 questions, and first let me tell you what the questions are about. Not what they are, but what they are about. And question 1 is, give acceptable names for the following compounds. So question 1 is names, and I've given some structures. And obviously the only structures that I can give you, because they're the only ones that I've talked about, have been substances with a benzene ring and some substituents, and I'll deal with that shortly, and substances with one or more double or triple bonds in. The next question is about NMR, and I want to make sure that you know what a coupling constant is and what a chemical shift is. So this is J values, and delta values. And question 3 is also about NMR, but it's how many signals By the way, I heard this afternoon that some of you sitting a little bit back there can't see the writing. You must shout out so that I can write bigger. You guys are paying money. Makes no difference to me if I write the letter this big or that big. So if you can't see, just let me know so I can write bigger. This looks nice and big to me, but of course I'm standing very close. How many signals for a particular structure? The sort of thing that I mean there, obviously, just let me make sure I haven't given you this one in the exam. No, I haven't. See, there are 2 methyl groups there. It gives only 1 signal. It's that sort of question. And then question 4 is also about NMR. And then it asks you, what's the structure of a compound that has the following NMR characteristics? So give structure, deduce structure, from proton NMR data. And then question 5 is I'll give you a benzene ring with 1 or 2 substituents on it, and an arrow, and then some conditions. And the conditions, since the only experiments I've described have been nitration, so comp nitric and sulfuric acid, or an acid chloride and aluminium trichloride for Friedel-Crafts acylation, or an alkyl halide and aluminium trichloride for Friedel-Crafts alkylation, or fuming sulfuric acid for sulfonation. There are very few that and bromine and ferric bromide for bromination. So I want to find out if you know what group will become attached to the benzene ring and where it will become attached. And I will go over all that today. And then, it's not quite the last question, it's aromaticity. In other words, I might write up, I'll ask you if that's aromatic. Well, of course it is. It's flat. And it has 4n plus 2 electrons delocalized over the whole perimeter. And question 7 is about Diels-Alder reactions. So what I will do in question 7 is I will give you some diene and some dienophile and ask you what's the Diels-Alder product. So you need to know how the diene and the dienophile approach one another, so-called endo-transition state. And then you should be able to write down the picture of the product. And the last question is about free radical bromination. Free radical bromination. So in other words, I'm going to question you on just about the principles of just about everything that I've covered, which you think I've covered a lot. And I've covered very little, actually. You guys don't realize that the information density per unit time in this course is actually low. Okay, so now you know what's on the exam. I know some people want to know how many marks for each question. I don't know why they ask me this sort of rubbish. It doesn't make any difference. Obviously, there are more questions on NMR than there are on other things, and the question that has the highest marks is the electrophilic aromatic substitution, this one. There are 18 marks for that. For the others, usually it's 10 marks or between 6 and 8. So if you can study only one topic, better study this. If you can study 2 topics, this and then NMR. Okay, so now you guys know roughly what's on the exam. And I won't auction the exam or the answers because you guys can't pay enough that would make it worth my while. Because I'd be fired, you see, so I'd have to have a lot of money so I would have to work afterwards. Okay, what I want to do now is more seriously, I want to go through and first of all give you a summary. I posted this on the e-class stuff. At least the person who I asked to do it says it's been done. I haven't looked. I don't know how to look. Yeah, you printed it. Okay. So it is available. I'm going to use that as my crib notes, and I'm going to give you a lecture on all the stuff there. So I have a very special computer. It can only access, with very few exceptions, the chemical journals. Nothing else like e-class, eBay, and web and stuff like that. It also has a link to the Nobel Prize Committee. There's a few good links. Okay, let me tell you now about NMR, what you really need to know about NMR. I spend a lot of time telling you about nuclei behaving as little magnets, and they can orient themselves with the field or against the field, and all sorts of stuff like that. Forget it. All I want you to know is to be able to look at an NMR spectrum, and together with a bit of extra data, to write down the structure of the compound. So I'm going to clean the board and I'll give you the essential pieces of information that you need to carry around in your head.
I hope this helps. I started my term paper yesterday.
Okay. If you look at an NMR spectrum, you will see a line on the right, which is the TMS signal, and you will see a bunch of signals that may be split somewhere along here, another bunch somewhere along here, another bunch somewhere along there. And each of these may be split. I'm not interested yet in what the splitting means. What this generally tells you is that there are 3 different types of proton in the molecule. So if you've got 20 bunches of signals, maybe there are 20 different types of proton in the molecule. If you've got only one signal, there's only one type of proton in the molecule. You remember I wrote up a few minutes ago, ethane, 2 methyl groups. I said there's only one signal. And ethane has only one type of hydrogen in it. Now I'll explain shortly why there's only one type of hydrogen. So the first thing that you notice is how many bunches of how many signals are there? Now admittedly sometimes it's not so easy to decide whether 2 things are actually one bunch of signals or 2 signals that are overlapping. But broadly speaking, the number of signals, I don't mean individual splittings, the number of signals tells you how many different types of hydrogen. And if you're trying to work out what the structure of a compound is, that's a useful piece of information. The next thing is there's a scale along the bottom, and it's given the symbol delta, and it's in a very funny sort of unit, it's not really a unit, called parts per million. And this position, the position on this scale tells you something else. It tells you something about the environment of the hydrogens giving rise to the signal. For example, if you see a signal at about 7, that almost always means hydrogens on a benzene ring. You don't have to worry about the explanation I gave you a couple of weeks ago about why it's down there. That's where it is. If you see a sharp signal at 2.1, that's almost always a methyl group on a carbonyl. So that is the position for acetone. So the position on this delta scale tells you something about the environment of the protons giving that signal. Now, it's not much use to you if I tell you it tells you something about the environment. Big deal, you still don't know what the environment is. But there are tables, and at the end of this exam paper, I typed it up myself. I have a list of some characteristic chemical shifts and the corresponding environments. So you don't have to remember this stuff. What I did is I took your textbook and I typed it up in a slightly different format because there are new rules about copyright and all that sort of stuff. Then I've also got one for infrared absorptions, because I did mention a little bit about infrared. You've probably done, you certainly should have done it last time. So if you look at the tables, you will see that down about here, always aromatic protons, and aldehyde protons come at about 9.5. So if you see, for example, a signal at about 9.5, you should think of the possibility that an aldehyde is present. So this is what the position on this horizontal scale tells you. It tells you something about the environment of the hydrogens producing the signal, and exactly what it tells you, you can deduce from tables. And I've given you a little table in the exam so that you don't have to memorize it. The other thing you'll notice about all these signals is that they have been, as we say, integrated. In other words, the area underneath the line has been measured, and it's all been normalized. And so if this is, say, 3 to 3 to 2 to 1 to 1, you know that the relative number of hydrogens here is 3, and it's the same as relatively as that, but this is only 2/3 of it, and this is 1. So this might actually correspond to 6 protons, and this to 6 protons, and this to 4 protons, and this to 2 protons, but the relative numbers is 3 to 3 to 2 to 1. So what this integration tells you is another piece of information, the relative number of hydrogens giving the signal. Now that's a very useful piece of information because supposing you know the molecular formula, and supposing you know that there are 20 hydrogens in the compound, if you add up these relative numbers and they come to 20, you know that not only are they relative numbers, they're the actual numbers. But if you add them up, they come to 10, you know something else, you better double them. So if this thing is a methyl group, you know there are 2 methyl groups. And since they both give the same signal, they obviously have equivalent protons. So the relative number helps you. That's a big help if you also know the molecular formula. Now generally speaking, when you have to interpret an NMR spectrum, you actually do know something else about the compound. You see, in real life, if you are a professional chemist, and you have a compound, which you might have isolated from a plant, say, maybe you knew that in traditional Chinese medicine, such and such a plant was good for rheumatism. There's supposedly there are plants like that. And so you extracted this plant, you chopped it up, you stirred it with ethanol, you filtered the gooey mess that you got, you evaporated the ethanol, and then you did what's called chromatography, and you got various fractions, and lo and behold, one of them was nicely crystalline. And so you ran an NMR spectrum. What you do at the same time is to run something else, maybe an infrared spectrum, or something called a mass spectrum. And those other things, and you might even have it analyzed. You could do what's called a combustion analysis, find out percentage of carbon, percentage of hydrogen, percentage of nitrogen, and so on. And those of you who were in my class last term will know how to do that. So you always have other, in real life, you always have other information. The only time you don't have other information is when you're doing a school exercise and the teacher just wants to see if, just with the NMR spectrum, you can work out what the likely structure is. But in real life, that doesn't happen. You almost always have other information. So the number of different signals is a guide to how many different types of protons you have. The relative intensity or area under the signals, not the height, the area, that tells you the relative number of hydrogens. If you actually know the molecular formula, you can then deduce what the actual number of hydrogens is. The position of the signals tells you something about the nature of the hydrogens giving the signal. Is it an aromatic hydrogen? Is it a methyl group next to a carbonyl? Is it an aldehyde hydrogen? And so on. Something else you need to know, there are various expressions that people use. Anything this way is upfield, and anything that way is downfield. You don't need to know why it's got that name, you just need to know it. Now, I want to run this out, and I want to draw now something to show what's called spin-spin splitting. You will often find that the individual signals are actually composed of a fine structure. For example, you might see see a pattern like this, where this is a triplet and this is a quartet, and the relative intensities follow the Pascal triangle, which you know is 1, 1, 1, 1, 2, 2, 1, 1, 3, 3, 1, and so on. Now, how do you work out, also, what can you deduce from these things, from this pattern? See, I regard this as a signal, and it's got some fine structure, it's a triplet. This is another signal, it's got some fine structure, it's a quartet. From the position of this and this, I should be able to deduce something about the environment of the compound. If this is a very high field, and this is, say, 3 or 3.5, means probably these signals, if I look at the tables, are next to a heteroatom, like oxygen. Now, there are a few things to notice about this. This gap here, J, is the same here, it's the same there, it's the same there, it's the same there. So if this is split by the signals here, this is split by the signals there, they share the same spacing, which is called the coupling constant, J, and it's measured in hertz. Now, the number of components of these splittings, in other words, is it a doublet, is it a triplet, is it a quartet, is given by a very simple rule, and the rule is n plus 1. So, if you have, for example, if you have this situation, and what's on here, which I haven't specified, is something that doesn't give an NMR signal. That means that this HA is not split by anything except this hydrogen. Then, if you want to work out the splitting of this HA, the number of vicinal hydrogens, that is hydrogens on the next door carbon, is equal to 1. And 1 plus 1 is equal to 2. So this thing would be a doublet. If I have something a bit more complicated, where the things that I haven't specified here are again things that do not give an NMR signal, and the things I haven't specified here are again things that do not give an NMR signal, then this will be split by that, and only by that, and that as well. So this thing is next door to 2 vicinal hydrogens. So n plus 1 is equal to 2 plus 1, which means that HA comes out as a triplet. And finally, you guys at the end there, highlight on this board, can you see? You sure? Okay. Again, what I haven't written here is something that doesn't give an NMR signal. So there's no splitting due to it. So this thing is split only by these 3 hydrogens. So here, n plus 1 equals to 3 plus 1 equals to 4. So HA comes out as a quartet. In this case, of course, this is split only by that. That's 1 hydrogen, 1 vicinal hydrogen. So n plus 1 equals 1 plus 1, so this is a doublet. So the nature of the splitting, in many cases, but not all, but for you, almost all, maybe absolutely all, the number of components in the multiplet tells you how many adjacent hydrogens there are. Now I'm going to give you some work examples, not taken from your textbook. I'll do that in a moment. There's something else you need to know about the chemical shift. You need to know how it's defined. That's how it's defined. So if you're using a spectrometer, let's say, that's 300 megahertz, that's 300 times a million. And you want to work out delta, and supposing the chemical shift from a reference, which is TMS, just supposing it's 2181 hertz, you multiply that by 10 to the 6 and you get an answer of 7.27. And supposing this is actually the signal position for benzene. Now you have used what is called a 300 megahertz NMR machine, quite expensive. But supposing you're working in the University of Timbuktu, they're poor. They only have a 60 megahertz NMR machine. If you run the benzene spectrum on the 60 megahertz NMR machine, you will find that the chemical shift of the aromatic hydrogens downfield from the TMS signal is only 436 hertz. So 436 hertz times 10 to the 6 over 60 megahertz. Guess what? Comes out at 7.27. And the whole purpose of having this funny scale is that if you quote the delta value, it doesn't matter whether you work in the University of Timbuktu or whether you work at the U of A, where we've got huge machines. Not the biggest, but pretty big. So that's the purpose of having this rather unusual method of measuring the position on the horizontal scale. Now there's something else you need to know about why I'm telling you this. There are 1, 2, 3. There are 3 unknowns, or 3 things in that equation. Obviously, if you know any 2 of them, you can work out the remaining one. So if I were to tell you that I got some compound and it shows a sharp signal at delta such and such a number, and I'd run it on a 800 megahertz NMR machine, and I ask you, what would be the chemical shift in hertz downfield from TMS? You plug in the number here, you plug in the 800 times 10 to the 6, you plug in 10 to the 6, and then you solve for this. If you can't solve a simple equation like this, big trouble. Big trouble. So this is the definition of chemical shift. You can see from the illustration that I've given you that one of the reasons for having this definition is that the chemical shift becomes independent of the instrument, which means that you can give characteristic data for a compound, whatever sort of instrument you use. The other thing that it helps you to do is, if you know all but one of the unknowns in that equation, you can work out the remaining unknown. It's sometimes useful to do that. Now, I said that one of the questions would be, how many signals would a particular compound give? And this is where you need to be able to judge whether certain hydrogens are the same in the sense that they have the same chemical environment. And there's a very, very simple test that always works. And the test is the following. If you got 2 hydrogens, or even more than 2 hydrogens, and you're wondering whether they are the same or in the same environment, because if they are in the same environment, they will not split one another. Now that may seem strange to you because logically, let me just draw mumbo jumbo I told you about little nuclear magnets. Obviously this hydrogen must sense the direction of the nuclear magnet of that hydrogen and of that one. And yet, unlike all the other cases, this is not split by that. So what is going on? Am I telling you a load of rubbish? Or is there something deep going on? There's something deep going on. If you do, which I'm not capable of doing, I hope I'm capable of learning if I needed to, but I can't do it here and now in front of you. If you do the quantum mechanical calculations, it turns out that the energy transitions that are involved in splitting are forbidden in cases like this. So they don't occur. It's not that this hydrogen doesn't see the nuclear magnets next door to it, it sees them. But there are very strange things that go on in quantum mechanics. We don't have to worry about it. There's a very, very simple rule that helps you decide if two or more hydrogens are in the same environment and therefore will not split one another as far as the spectrum is concerned, as far as what you see. And the rule is that you just write down, supposing there are two hydrogens you want to think about. You write down a picture of the compound twice. And in one of them, you replace one of the hydrogens by some group X. And in the other picture, you replace the other hydrogen by some group X. Same group. And then you just ask yourself, are the two pictures the same? Are they enantiomers or are they diastereoisomers? If they're the same or if they're enantiomers, there is no splitting. If they're diastereoisomers, there is splitting. That's the rule. Very simple. It always works. That sounded almost, but not quite, like a very small World War II pistol. It was silence. Perhaps it was a Beretta. It was silence. Being probably a little loud. My favourite pistol is a Browning Mark IV, which is a British Commando in World War II, made in Canada.
I haven't seen him today.
I don't like firing it too much because it's a little bit big for my hands. My thumb gets quite sore. Don't worry, I haven't brought one in, so if any of you are not attending, you're quite safe. Okay. Let me give you some examples of this simple test.
You put cover with an X, right? Cover reading.
We've got three fancy words to deal with these three situations. If you do this replacement business, which I'll illustrate in a moment, and the compounds are the same, you say the hydrogens are homotropic. If the compounds are different, the hydrogens are heterotropic. And if the compounds are different, but the compounds are diastereoisomers, then the hydrogens are diastereotropic. You don't have to worry about the names. All you want to know is if you're dealing with two hydrogens and you do the replacement of each by the same group, are the two things the same? In which case no splitting. Are they enantiomers? In which case no splitting. Or are they different compounds, including diastereoisomers? In which case there is splitting. So let's have a look. So I've got a few problems here. I've got 6 hydrogens. So let's take it in 2 lots. What about these 3 hydrogens themselves? You know that there's pretty rapid rotation around that central bond. So if you replace one of the hydrogens by group X, and And then over here I write another picture in which I've replaced that hydrogen by group X. And over here I write another picture in which I've replaced this hydrogen by group X. Because there's essentially free rotation about that single bond, in every case you can rotate the picture so that they all look like this. And so whichever of these three hydrogens you actually replace, you actually get the same compound. Therefore, these three hydrogens do not split one another. Now we've got another question. Do these hydrogens split out? Well, it's very easy by this test that I've given you. Let's replace one of them by bromine, and now let's replace at the other end by bromine. You know, if you can't recognize that this is the same compound as that, you want to transfer to country dancing 101. And so, obviously, these hydrogens are the same as those hydrogens. So all the hydrogens here are identical. Therefore, there's no splitting. So you get only one signal. Now let me give you a slightly more complicated example. So we've got, I'm going to give you the answer straight away and then I'll explain to you. We've got a CH3 and a CH2. So we'd like to know if this type of hydrogen is different from that. Well, obviously, if you replace one hydrogen here by, say, bromine, and you replace in another molecule one of these hydrogens by bromine, you're going to get different compounds. So this CH2 is different from this methyl. The next question is, are these hydrogens in the methyl group all the same? Well, I've given you that answer already. They are the same. What about the hydrogens here? Well, let's do the test. Here's a picture of the compound, and I want to know if HA, let's call it A, let's call that B. I want to know if HA and AB will split one another. And so let me replace HA by something. We replace it by X. Now let me replace HB by something. Those two are enantiomers. They are mirror images of one another, not superimposable. And therefore, those compounds are what are called enantiotopic. And they do not split one another. Now let me give you one more example. So if I ask you, how many signals will this olefin give you? Well, obviously, there are 8 hydrogens there, so you want to know, you're going to get 8 signals, maybe with some fancy splitting, or will you get something less? Well, this methyl group, if you do this substitution business, first of all methyl hydrogens, all the 3 hydrogens on the methyl group, they're always the same, so you don't have to worry about that. Is this methyl group the same as this one? Well, if you do a replacement, supposing you replace this by X, and then draw another picture and replace this by X, you're going to get the same compound. So this methyl, the hydrogens on it do not split that because they're the same. Likewise, this hydrogen does not split that one for the simple reason. Then you replace them so you can actually see. Let's replace it by deuterium. two pictures, A and B. If I lift A out of the paper and flip it over, put it on B, it's the same thing. You're looking puzzled. You agree it's the same? So don't look puzzled then. I want to show you now something that's a bit more complicated, where the hydrogens are actually diastereotopic and where they will split one another. If you find what I've told you difficult, there's a no-brainer way of using the information. You can bring molecular models in. If you build a model, don't pass it to the guy next door. You know, you make some compound, pass it. You mustn't do that. There are rules against that. If you find what I told you difficult, you just can't visualize it, you make a model of one replacement, you make a model of the other replacement, you hold it in your hand, see if you can superimpose one on the other. If you can, you know they're the same. If you can't, you know they're different. Okay, I've got now two hydrogens that I've called A and B. And the question is, are those two hydrogens, as was the case with this, these two hydrogens do not split one another. Question is, do these two hydrogens, after all they are a methylene group, just as here, do they split one another? The answer now is yes. Because if you do this test, if you replace, let's replace HA first of all, let's replace it by deuterium, so we've got H there, and now let's replace the other one by deuterium. These two compounds that I've now drawn, A and B, are what are called diastereoisomers. And you should remember from last year's course that diastereoisomers are stereoisomers that are not enantiomers. I know that sounds kind of complicated. Let me just refresh your memories about isomers. There are many, many compounds, or many, many cases, we've got two or more compounds that have the same molecular formula, but they're different compounds. We say that those different compounds are isomers. Now, isomers can differ from one another in various ways. The actual connections between the atoms can be different. In other words, in one case you could have two carbons in a row joined to an oxygen. In another case you could have a carbon joined to an oxygen joined to a carbon. Those are called structural isomers. There's another group of isomers in which the connections between the atoms is the same, but the shape of the molecule is different. In one case an OH group might be pointing that way, in the other case it might be pointing this way. Those are called stereoisomers. Now, stereoisomers are divided into a number of groups. If the two stereoisomers are related as an object is related to its mirror image and are not superimposable, those are called enantiomers. And stereoisomers that don't have that relationship are called diastereoisomers. And these two babies are not related as an object is related to its mirror image, but they are stereoisomers because they differ in shape. They all have carbon attached to carbon carrying one deuterium and one hydrogen. Carbon attached to carbon carrying one deuterium and one hydrogen. This carbon attached to carbon carrying an OH and a hydrogen and methyl. This carbon attached to carbon carrying an OH and a methyl, so forth and so on. So the connections between them are the same. The shape of the molecule is different. And so these are stereoisomers. And they are not enantiomers. Therefore, by definition, they're diastereoisomers. So these two are diastereoisomers, which means that HA and HB are what we describe in the NMR language as diastereotopic, and therefore they will split one another. There's a couple more things that you need to know, and that one of them is that if two hydrogens are splitting one another, this will be split into a multiplet with a certain coupling constant. This will also be split into a multiplet with the same coupling constant. In other words, if A and B split one another, and the coupling constant for A is 3.5 hertz, the coupling constant in the signal for B will also be 3.5 hertz. And if you've got a signal that's got a coupling constant of, say, 3 hertz here, and another signal's got a coupling constant of 6 hertz over here, they ain't coupled, not to one another. This is coupled to something else, this is coupled to something else. So the coupling constants are the same in mutually coupled protons. One other thing that you need to know about coupling constants, and it applies very frequently to six-membered rings. It actually applies to everything, but you very frequently meet it in the case of six-membered rings, and that is that if you're dealing with hydrogens that have a dihedral angle of 180 degrees, then the coupling constant is usually quite large. And by large, I mean 10, 12, something like that. And if you're dealing with hydrogens that are, say, at 90 degrees to one another, the coupling constant is very small, close to naught. And if you've got something in the middle, say 60 degrees, it's small, 2 or 3. So, for example, A, B, and C, the JAB is big, and the JAC is big. AC is big, and JAB, so maybe about 10, and this one, JAB, is about 2. So there's a dihedral angle dependence on the size of a coupling constant. And this is sometimes very, very useful when you want to assign stereochemistry in a six-membered ring. Now, there are some complications to all this. For example, just let me make sure I get the right example. Yeah, this is fine. These hydrogens, at first sight, appear to be flanked by 3 hydrogens on one side and 2 hydrogens on the other side. In other words, 5 hydrogens. And so you are tempted to apply the n+1 rule and say that those 2 middle hydrogens would be split into n+1, 5 + 1 into 6. Now that is true if and only if the coupling constant between these hydrogens is the same as the coupling constant between the other pair of hydrogens. If that situation is not true, then the splitting is more complicated. But you don't have to worry about that. Okay, and I think there was only one other thing that I told you about NMR that you need to have in your mind, and that is that OH groups for alcohols you see, as far as these hydrogens are concerned, this is a vicinal hydrogen. And you know that in many cases, if that CH2 group was flanked on one side by one vicinal hydrogen, it would be split by that hydrogen into a doublet. The reason being that that hydrogen, acting as a little magnet, could have the magnet aligned with the applied field or against the applied field. So in one situation it would help the applied field, increase it. In the other situation it would decrease it. So the CH2 would see two different fields. However, in alcohols, the oxygen on the hydrogen is actually normally, unless the alcohol is very dry, the hydrogen on that oxygen is changing partners, like what goes on in Hollywood. It's changing partners very quickly. And so what this sees is a sort of average orientation of this nuclear magnet. And this nuclear magnet can only be with the field or against the field. And an average of that is nothing. So this does not sense any disturbance, any increase or decrease of the applied field due to the presence of this, because this is exchanging very quickly. So in the case of alcohols, it also applies to NH compounds. You don't normally get splitting from that hydroxyl proton or the NH proton. If you want to observe that splitting, you must take special precautions. There's some solvents that are better than others. Everything's got to be very dry. You mustn't have any acid or base present. That is the last of the things that I needed to tell you about NMR, but the key thing I haven't told you, because I haven't really told you, and I'm now going to, I can't really tell you, but I can show you how to do it. I haven't really shown you how to take some NMR data and produce a structure. I've given you a quick rundown of the theory. Now I'm going to write up, I'm going to put a spectrum up on the board, and I'm going to show you how one would go about deducing the structure, which is probably the thing you most want to know, because you're all scared that this is going to be an exam. It is going to be an exam, but I'll tell you how to do it. Do you have a question? Yes, I will give you the information, don't worry. I'm very kind, I'll give you every bit of information you need except the answer.
How long is this going to be? It's already been an hour. You just went over that.
Later, I leave the longer.
Yeah.
Because I'm about to stop running.
Supposing this is the NMR spectrum, and the question is, and that's the formula, C4H10O. Now, the way to do these things is to look in turn at each of the pieces of information that you have and see if you can draw some conclusion. If you can't, you move on to the next piece of information and see if you can draw some conclusion. And you go through until you've examined every piece of information that you have. Then you go back to the beginning again. And of course, when you go back to the beginning, you now know a little bit more than you knew a few minutes ago. And you ask yourself the same question. What conclusions can you draw? And you keep doing this. And every time you go through these iterations, you'll get more and more information in your mind as to what the likely structure is. Now, We know the formula C4H10, 3, 4, 5, 6, 7, 8, 9, 10. So, probably there are indeed only 3 protons, 2 protons, 3 protons, 2 protons. We know what the formula is. The number of double bond equivalents is 0. So you can't have any rings, and you can't have any double bonds, and you can't have any triple bonds. We notice that there is a triplet at quite low field, and we know that there is a heteroatom, oxygen. We also know that when you have a CH2 group next to a heteroatom, comes lower field. So possibly this is next door, represents protons on carbon, 2 protons, next door to a heteroatom. Well, we've got only one heteroatom, so maybe we can start to write a piece like this. Oops, sorry, not 3, 2. We also know at quite low field we've got a 3 proton singlet. So it isn't split by anything. And it's sort of middle of the spectrum. You look in the tables, again, that usually means a methyl group attached to a heteroatom. We've got only one heteroatom. It's oxygen. So maybe we've got an OMe. Well, since we've already used up the oxygen because we think we've got a CH2, so now we have a methyl ether with a CH2. We notice this CH2 is split into a triplet. So maybe it's next door to another CH2. We also notice we've got a triplet at very high field. You look in the tables, that's 3 protons. It doesn't require a lot of brain power to suspect that a 3 proton signal means a methyl group. So maybe we've got a methyl group at the end of the chain. Now we've got 4 carbons, 1, 2, 3, 4. Now guess what? This, you see, would certainly be split in by this, and it would be split by that. It actually sees 5 vicinal hydrogens, and if the coupling constants here and there are the same, then we see 6. 1, 2, 3, 4, 5, 6. So that is a possible structure for the compound. And that indeed is the structure of the compound. So what did I do? I looked at the formula. I recognized there was no double bond equivalence, which means no rings, no double bonds, no triple bonds. Since there are actually only 4 carbons, it doesn't require a lot of effort to write down all possible structures. But I didn't want to do that. It's sort of cheating because it means that if you get a more complicated case, 10,000 possible structures won't be able to do it. So I looked at the spectrum and I saw a few things that are characteristic. I saw sort of 2 signals equal to 3 hydrogens. As soon as you see that, you must suspect methyl groups. They don't have to be methyl groups, but always, as the Canadian police say, a person of, what are the words they use, person of interest, when they're looking for somebody? In England, the police use a different form of words. If they've arrested somebody, the gentleman is helping the police with their inquiries. They don't believe he's a gentleman, but that's another story. As soon as you see a 3 proton signal, a possibility of interest, shall we say, is that it's a methyl group. If it's a singlet, it's probably an isolated methyl group on something that doesn't produce any splitting. If it's downfield, it's probably on a heteroatom. If it's upfield, and if it's a triplet, it's probably next to a CH2. So I worked along those lines and you can get out the structure. Now let me do another one. So here's a compound, it's got the same formula, C4H10O. It's got only two signals. Each is a signal. The fact that it's got only two signals tells you, very likely, there are only two different types of hydrogen. One of the signals is 9 hydrogens. Now, you don't have to be as smart as Sherlock Holmes to realize that if 3 hydrogens are suggestive of a methyl group, 9 hydrogens are suggestive of 3 methyl. And so the first suspect is that you've got 9 equivalent hydrogens. There's only one, well, there is one very common way of getting 9 equivalent hydrogens, and that's a tertiary butyl group. You have 1 oxygen, and you have a singlet. And this formula fits the bill. You know from what I told you that OH signals can come over a very wide range. In fact, this is the spectrum of tertiary butanol. Now I could have approached it a little bit different, C4H10O, no double bond equivalents, therefore no rings. There are only 4 carbons. There's a very limited number of ways in which you can arrange 4 carbons without having a ring or double or triple bonds. And one of them is that way. And since there's no splitting between the signals, this is the only reasonable structure. Now, this compound clearly has 2 different types of hydrogen. And the relative areas is 3 to 2. You add 3 and 2, you get 5. But the molecular formula is 10 hydrogens. So whatever it is that's giving rise to the high field triplet, there are 2 of them. And whatever it is that's giving rise to the low field, middle of the field quartet, there are 2 of those. There are no double bond equivalents, and we have 1 oxygen. Now, a triplet quartet pattern, in which the quartet is 3-ish or middle of the spectrum, is almost always indicative of an ethyl group on a heteroatom. We've got only 1 heteroatom, so we can write down this, and now obviously we have to double it. And you can see if you do this replacement test I gave you, this methyl is the same as that one. This CH2 is the same as that one. So the signals for this will be the same as the signals for that. And therefore, that is the answer. Now there's a harder one. You notice how I go about it. I look at various things and I don't say it's definitely. It's suggestive of so and so. And I don't know if you realize this, but if you're in a court of law and somebody's being accused of something, and there's a bit of evidence that suggests that he did do it, but it's not watertight. And there's another bit of evidence that he did do it, again it's not watertight. And there's yet another bit, again not definite. Although the individual bits are not absolutely 100%. Once you've got enough of them, they're all pointing in the same direction, you know the guy's guilty. And that's how British and Canadian justice works. Very good it is too. So once you've got little things suggesting certain things, it all fits. You know you're on the right track. Okay, so what is the structure of this compound, C4H8Br2? You notice the first thing they always do is to find out how many double bond equivalents are represented by the formula. And those of you who were in my class last term, you know there's a magic formula that always works. And if you apply that magic formula, you can get the answer 0. So there are no double bond equivalents in this. So there are no rings, no double bonds, no triple bonds. You have a 6-proton doublet. When you see 6 protons, you need to think of the possibility that there are 2 methyl groups. And because it's a doublet, each methyl group is probably split by 1 hydrogen. Now you notice also that there is a quartet, quite low field. And you know that when you get signals low field, one of the possible things is that the carbon carrying those hydrogens that you're looking at is attached to an electronegative atom. We've got an electronegative atom here, got 2 of them. So we think that there's a methyl group next, don't let me write this deep, it's not very deep. We think from the doublet that there's a methyl group next to 1 hydrogen, and that hydrogen, we think, carries an electronegative atom because the position, the chemical shift is quite low, and that hydrogen, of course, would be split into a quartet by the adjacent methyl. So we've satisfied the quartet, we've satisfied the doublet, this would certainly be a doublet, but we haven't satisfied the whole molecule, because we've only got half the structure there. If you think about it for a while, you will realize that it is a molecule with some symmetry in it. And this methyl group is exactly the same as this methyl group. And so this and this give just 1 signal. This likewise is the same as that. So these 2 give only 1 signal. So all you actually see is the signals for 1/2 in a sense. And it all fits, it all makes very nice, logic is beautiful. I'll give you one more example, more difficult still. Multiple. So let me just work out the formula of this thing. Just hang on a second. 1, 2, 3, 4, 4, 2, 3, 4, 5, 6, 7, 8. Oh, it's the same as the other. Now, hopefully, I'm bright enough to be able to work out what the structure is. No, I shouldn't say that because I've got structure here. It'd be cheating. Okay. We got a formula. We know that there are no double bond equivalents, so it's got to be a chain compound. No rings, no double bonds, no triple bonds. We notice something. We notice we've got some high field signals and some low field signals. One of the things we know about low field signals, those in the middle of the spectrum, is that they probably represent hydrogens on carbon attached to a heteroatom. Well, we've got some heteroatoms. So we expect one or more hydrogens on carbon attached to bromine. That's what we can deduce so far. We notice that there's a 3-proton doublet. As soon as we see a 3-proton doublet, there's a methyl group that's split by an adjacent 1 proton. So from this bit, we can probably write down with some confidence a piece like that. We also notice that we have a quite low field triplet. And a low field triplet for a molecule with that formula would be very nicely accommodated by this sort of structure, where that CH2 is a triplet. Now we know we've got only 4 carbons. 1, 2, 3, 4. So perhaps we should join them together. We've also got to deal with one more bromine. And if you put it together like that, you can now understand the spectrum. Here's a methyl group split by 1 hydrogen. Here's a methylene split by 2 hydrogens. I made a mistake. Better not have. That's I've drawn up the wrong. Yeah, I've drawn the wrong picture, I think. Hang on a second. No, I've drawn the right picture. 117. 2.3, 3.5, and a multiple. So let me just work this out. Hang on a second. 1, 2, 3, 4. So I have this.
Because it's more electronic. Huh? What? Sorry. Go
Just
ahead.
to work out a this book that I got it from is jumbled up the picture and the actual spectrum. Just getting on the second.
Wouldn't this be more
1.7.
Because like it's a here.
is
Makes no sense.
Oh, no, that's okay. Look. This is the doublet there. This one is the triplet there. This one sees 2 and 1 is 3, so it sees the 4 there. And this one is coupled there and coupled there. These couplings are not quite the same. So in the best situation, it would see 5, so it gets 6. They're actually not the same, so it's more complicated. So this fits in quite nicely. Okay, I think I've given you enough examples on how to assign a structure once you've given the spectrum and some other information. Now the other information might be a molecular weight, it might be an infrared spectrum. Supposing I gave you a compound with oxygen in, and I said there was an infrared absorption at 1730, wave numbers. You know, as a carbonyl then. So what you do, as I've said several times, you look at each of the pieces of information in turn and see if you can make some deduction. Do not try to squeeze every piece of information out of the first thing you look at, and then go on to the next piece and squeeze every bit of information out of the second piece and so on. That isn't the way to do it. You look at it, make a rough assessment. Oh, that's probably an ethyl group. Go on to the next piece. Yeah, this might be an ethyl group. Or, oh, it smokes, it can't be an ethyl group. You just go through like that, and when you circle through again, after you've done it a couple of times, you'll have the answer. Okay, let's now change gears and do something much easier. I talked about conjugated systems. Conjugated systems are simply to give you an example, systems in which there are alternate double and single bonds. If you have something like this, this is not double, single, double, single. This is not conjugated. These are isolated double bonds. And this is another type. These are cumulated double bonds. Cumulated double bonds. Now, what do you need to know about conjugated systems? Not a great deal. I told you that if you take butadiene and you treat it with HBr, you will get two types of product. And at a low temperature you get mainly this one, and at a high temperature you get mainly this one. And I explained it by telling you that the process was reversible at a high temperature, and I explained the formation of that by showing you that you can write a resonance structure, and that leads to that. That's one of the things you needed to know. The other thing you need to know that all these conjugated systems absorb UV or visible light, depending on how many double bonds there are. Ethylene itself, I think, absorbs 171 or something like that, and butadiene somewhat higher. But if you've got a lot of double bonds, like in a carrot, it absorbs in the visible wavelength region. The most important reaction, or one of the important reactions of substances with double bonds, I don't know why it's in the textbook under conjugated systems, but anyway it is, and that is the mechanism of allylic bromination, which you do with a compound called N-bromosuccinylide. And it's advisable to know the mechanism of this reaction. I'll show you how it works. Okay. This beast is N-bromosuccinimide. It's one word. And you mix it with your own thin, and here's my own thin. And you heat the mixture, or you shine light on it, or you do both. And some people add some dibenzoyl peroxide, a little bit of it, and other people add a little bit of this compound. And what you get out of this is the alignic bromination product. And the question is, how does this work? And it was a very famous experiment done many, many years ago by a man called Goldfinger. Not the one in the James Bond books. And what he did is he proved that what is happening is that a very, very low concentration of bromine is being generated in the system. And it is this very low concentration of bromine that is actually causing or giving rise to this alignic bromination product. I won't tell you how he did the experiment, that doesn't matter. But what we need to find out is how are we going to get from this mixture a low concentration of bromine? Well, there are several ways, and it all depends on exactly how you do the experiment. Quite often, N-bromosuccinimide contains a little bit of HBr in it. If it's not 100% pure, frequently it isn't 100% pure. It actually works like a charm. So what goes on in that case? What goes on in that case is this. I won't worry about the other component that's formed. Well, maybe I should tell you what it is. It does not survive like that. It immediately changes. To this. But the essential thing is that you now have a little bit of bromine in there. And what the bromine does with the heat or the light, it gives two bromine radicals. I'm sorry, did somebody have a question? I heard some vocalization of some words that I didn't quite catch. There seems to be in English there. You get two bromine radicals. Now, I will clean this off if necessary. I'll write it up again in a moment when I come to tell you what the story is with dibenzoyl peroxide and that other substance that I wrote down. So what do the bromine radicals do? So the bromine radicals remove a hydrogen from the alignic position, teas. They're very famous British cooking. You get an allylic radical. The allylic radical attacks bromine to give you the product out of bromide, another bromine radical. The bromine radical then attacks another molecule, as I've shown here, and it keeps going on. And this HBr reacts with another molecule of N-bromosuccinimide to make a little bit more bromine. Now there are some termination steps as well, but this is the main process that goes on. Now the question is, why do some people use dibenzoyl peroxide, which was one of the other ingredients that I wrote up? Well, it's possible to explain what is going on there.
I can't get a ride today. So you just went home?
Dibenzoyl peroxide attacks the N-bromosuccinimide and generates a bromine radical. The bromine radical then abstracts an allylic hydrogen to give you HBr and an allylic radical. You know what HBr does to N-bromosuccinimide? Generates more bromine. So by adding a very small amount of dibenzoyl peroxide, you start off this radical business and you generate Br dot. In exactly the same way, if you use this compound, which I perhaps didn't tell you about in the past, if you heat this stuff, nitrogen plus this carbon radical. And this carbon radical just adds on to N-bromosuccinimide in the same way to generate some bromine radicals. So that's the story. N-bromosuccinimide requires a little bit of HBr to generate a low concentration of bromine. And once you have a low concentration of bromine, you can carry out the allylic bromination by this radical chain mechanism that I gave you, and that I think you've also had in 10261. There are some variations of this in which people add dibenzoyl peroxide or that material. These are called initiators. Sometimes it's not necessary to add that. Many of these experiments are done, of course, by people who really want the reaction to work, and so they know that heat and light are necessary, so they added an initiator as well to give another pathway of making the bromine radicals. So they just add everything, hoping that one of the possible mechanisms will prevail and give them what they want. So that's the story for allylic bromination. I then went on to the business of writing resonance structures. I'm soon coming to the end, don't worry, so we'll do no doubt getting lessons. some rules that you must obey. And one rule is that only electrons can be moved. You can't move atoms. Only electrons can be right. Only electrons can be moved. The other thing is that all the resonance structures must have the same geometry. You can't change the shape of the structure that you're writing. And all of the structures must be proper Lewis structures. You can't have bizarre numbers of electrons surrounding various atoms. You have to have the correct number. And another requirement is that the number of unpaired electrons in every structure must be the same. So, for example,